here the different images of different cities in terms of different meanings and definition that I myself made like for myself, like this is a package of different images in terms of different cities, meaning like there are utopias here, dystopias, and reality. And I was wondering that actually this is the reason that I'm in this workshop, to see if it is any possibility to have AI and machine learning science in kind of cities, like in developing country cities as well, not just focusing these kind of approaches in first world countries as well. Thank you.
Great, very thoughtful. Thank you. And Van Rong Miao.
Yeah, and you can call me Mela. Hi, everyone. I'm Mela and from the middle of China. And right now I'm living in the United States and studying at University of Michigan as an urban design student. I took it in my living place called Elmer. Due to the COVID-19, I cannot go back to my hometown. So I had picnic meetings with my colleagues and professor every week. Then I took it in during this trip. I want to record it every time in this special situation, you know that. So thank you. And it's so exciting to meet all of you. Thank you. Thank you all.
Thank you too. And Artyom?
Hello, everyone. I have chosen this picture because it's I'm always happy to see some mistakes, and at the same time these mistakes sometimes shows us hidden layers, and it's also somehow correlates with the machine learning and with the topic that we will explore in this workshop. So yeah, it's a picture from the main train station in Amsterdam. So I found it quite interesting and suitable for our context. Yeah, thank you.
Yes, thank you. It's very appropriate. And Edward? Edward here? Anyways, it's a nice picture, beautiful landscape. Anastasia?
I'm here. Hello, everybody.
Okay, sorry.
My name is Anastasia, and I'm from Minsk, and I study architecture in the Russian National Technical University. I chose this picture because it's a collage, because it's how I see my part of the city where I live for 5 years, and I always, when I go for a walk, I always try to find some things that inspires me, and that's how they look together.
Yeah, we can hear now.
Okay, sorry. Do you hear me now?
Mm-hmm.
Yeah, okay, sorry. Sorry. So I'm Edward, I'm an architect from Vienna. And so besides my passion about architecture and all sorts of optimization and that stuff, I'm also passionate about photography. And this reminds me that I took that in the Adriatic Sea, and it was very interesting because I woke up very early in the morning before the whole seafront got crowded to get this very, very empty scenery. And yeah, it reminds me of that Le Corbusier definition of architecture, that light makes it see. So the combination of light, which makes matter appear. And this also relates to all the energy performance investigations I'm doing in my PhD, because light is like the source of light general in a multiple ways. And yeah, and besides that, I'm working at an engineering consultancy, developing tools for urban master planning, so focused on digital stuff to help them in infrastructure questions, demand estimation, and all that stuff. Okay, thanks.
Thank you. And Effie?
Yeah, this is me. This is a sunset in Thessaloniki, a city in North Greece, where I am from, and where I studied architecture. And I picked this image that's because it's meaningful to me in many ways, not only the memories of that day, but also the feelings that this view creates. It is in the seaside when you leave the city on your back, and you face this view, and you can forget the dense urban environment and the noise and any problems, and just yeah, enjoy the view. And yeah, that's it.
It looks very peaceful. Thank you. And
yeah, I'm here. Can you hear me?
Yes.
So I'm Svonko. I work in the lab in the BTU in Cottbus in Germany. I'm an architect and computational designer. And this picture is the perfect atmosphere after sitting the whole day in the lab. And you need to just go and forget about the lab and go have a beer or chill or something. And beer is a nice activation function too. So it just brings happening. So that's what it reminded me of.
Nice setup.
Yeah. Yeah, I'm in the lab now. So.
And Abel? Or Abir?
Here, are you here?
Okay, we continue if you come.
Salam, can you hear us? Let's continue.
Yeah. Bianca?
Hi, I'm an undergrad student from Mumbai, and this picture was actually taken when I was doing my internship in this large slum called Dharavi, and I was conducting a research about the fisher village within Dharavi and how they used to fish in this pond that was actually contaminated by all the development that you see behind. This is sort of what inspired my thesis that I'm conducting right now on urban coastal resilience and how you sort of balance this development and ecological systems and all. That's
Great.
all.
Thank you.
If we could just go backwards, a beer is here, I believe.
Yeah, great.
Okay.
Abir?
Hello.
Hello.
Yeah.
I hear you.
I'm Abir Salim from Egypt, from Cairo. And after I come, I'm architect and I'm doing my master's thesis in Berlin, in TU. I came here after the lockdown, no, before the lockdown by 2 months, by 2 weeks. So after I come, everything is strict in Berlin. No one can go any place. So this photo after the lockdown is already mitigated in Berlin. And here in Berlin, all people save the all restrictions and the counts without any restriction and anything. So this is this photo after the lockdown by 1 day. The people didn't go in the streets and me only on the street after the lockdown.
Nice. And you're not wearing a mask.
Yeah.
Eva?
Hi everyone. I'm Eva from my research about thermal comfort and energy in the open spaces. I picked this thermal comfort and shading, radiation, and other things that I'm doing in my research to learn everything about AI and machine learning in this workshop to do my research as well as I can. I'm super excited to join with you.
Thank you. I'm glad to have you here. And now Christina.
Hi, I'm Christina. I'm an architect and a researcher currently doing teaching and research at EPFL in Switzerland. And this picture image is not mine, I didn't take that, but is where I go during the summer for a couple of weeks. It's a small island in the Cyclades. And yeah, this is the first thing that came into my mind when you asked for a picture.
Great. And Javier or Javier?
Hello. Hello. Can you hear me?
Yes, we can.
Okay. So hello everyone. I'm Javier. I'm an architect and planner, urban planner from Madrid. As well, I studied computational design eventually because I've been using for years big data applied to design and computational techniques applied to building and urban planning. And this image actually comes from my very last project when I was studying my master's in Pittsburgh at Carnegie Mellon. It's on one hand, I mean, I don't know if you're familiar with photogrammetry when you are generating those textures for mapping the images, but actually it combines for sure on one side the emotional part because it was a very good time for me there, and you can recognize chunkies of the place in a very weird way, but at the same time it represents pretty much a lot of the experience with computational tools when you apply to architecture and urban planning. On one hand, they facilitate, they free up your attention because it automates many of your very tedious tasks that you need to perform for doing design. But at the same time, their behavior sometimes are like black boxes. They are unattended that you don't know why they are behaving in that way, and you are not controlling the whole process, and it becomes very, very complicated to understand what's going on with those algorithms or those tools that you are using. And this is one of my biggest interests on researching about those topics, on uncovering that black box embedded in these tools.
Great, thank you for the insight. And the picture looks quite artistic. And Michael?
Hello, I'm Michael. From September, I'll be a master's student at the Manchester School of Architecture. The image in the picture here is Big's Maritime Youth House. I chose the image because I feel like it's a good example of the changing role of the architect and the value that a strong, clear idea can bring to a project. That's it. Thanks.
Thank you, Michael. And Dominique.
Hello, my video is a bit problematic, so I hope you hear me.
Yep, loud and clear.
Yeah, cool. So that's me in my quarantine space that I spent the last 2 months being isolated and just doing my semester's work for the school. That's it. Yeah, I'm studying now at KDK in Copenhagen at CITA, the Center for Information and Technology in Architecture. And currently I'm in Lithuania in still sort of quarantining, but not that much anymore. Yeah, that's it.
Thank you. So you had some productive time during quarantine?
Yeah, a little bit.
And KR?
Everyone, I'm Kier. I'm an urban designer based here in Manila. And this photo was taken just before quarantine here. And before quarantine, a couple of trail running buddies of mine would run up the mountains and just see the city from there. And I just think it's a great reminder of the image of the city while we're all cooped up inside, an image outside our models and drawings. That's it.
Thank you. And we didn't receive some pictures, but if the participants are here, we would like to hear them. Sebastian?
Sebastian?
Hello. Hello, everyone.
Hi.
Share your screen.
You hear me? Yeah, glad to be here. Sorry, I didn't send the picture on time, but I'm an engineer, an architect. I'm from Paris, and I run a studio which is Echoes de Paris, where we work with architects, urban designers, and engineers on bioclimatic design and all sorts of subjects. Thank you.
Thank you. And Yun-Jan?
Yun-Yang?
She's in the attendees. I'll pull her.
Oh, yeah.
Promote to panelist.
Thanks, Navid.
Mm-hmm.
If anybody is stuck in the attendees and is actually supposed to be up here, raise your hand. We will see you and we will bring you up here. We can't check every name, unfortunately. Yun-Yang, can you hear us? Maybe we go on and we come back to you.
Can you hear me now?
Ah, yes.
Perfect.
Oh, great. I'm an undergraduate student from Nottingham, University of Nottingham, and is studying architecture instead of urban planning. So I'm just interested in this topic and want to participate in this seminars, lectures, and maybe seminars.
Great. Thank you, Yun-Yan. And we continue with Andy.
Yeah, hi everyone. Let me just share my image because I do
Yes.
have one. Admittedly, I shared it very late. Okay, can you see?
Yes. Can you see your picture?
Okay, brilliant. Okay,
and
so
where that is as well.
Excellent, good. So yeah, my name is Andy Watts. I'm the Director of Design Technology at Grimshaw. And that kind of, covers all manner of sins from BIM to computational design to digital fabrication and everything in between. And so, this image, I guess, is kind of a hero shot that that has actually been a great selling point for my team. And it's composed of two things. So the right-hand side is the canopy for the Dubai Sustainability Pavilion. And that canopy was basically designed with the single grasshopper definition of 2 or 3 people working into it. And then all of the stuff below it at ground level, you can see as, fairly rectilinear form, but was designed with 20 architects. So to me, this was kind of a winning thing of why computation is actually becoming more and more prevalent within architecture. And it's a great selling point for my team and computational design, I would say.
Thank you, Andy. Yeah, nice structure. It looks very convincing. And now we continue. So if there is anyone that we are missing that didn't have the chance to introduce, please raise your hand, right, or just come up here. I think.
I believe that's everyone.
Yep, that's everyone. And we continue with the presentation.
It was great to meet you all in picture form and in person form. So glad you're all here.
Yes. Yep. I hope we know a little bit more each other now, and we can continue
I will go on. Before I go on, how's everybody feeling? Everyone is okay. So say awake and like, you know, ready for a 4-hour like drill into like machine learning on a Sunday. Yeah, you can also do. There's certain things you can do in a Zoom meeting. You can do like some reactions. I think you can do reactions in here. I'm not sure because it's a webinar. Or at least meetings you can do reactions, or you can just like raise your thumb and say like everything is okay. The one thing that we really need to avoid is you know, this distance of the online kind of like meeting space oblivion. You know, like we are all essentially in our living rooms and we are not in an actual meeting room. But if we try to interact a little bit more, it would make really this workshop much more you know, much better. And so I again ask everybody to be more active and try to commit a little bit to this. I mean, everybody has their own, you know, kind of like way of doing this, but the more we do it, the better. So please unmute yourselves and shout anytime you want, you know, or like, you know, scream or like, you know, start like saying, you know, this is not good or this is great or whatever. Just please interact. So right now, I'm going to give a little bit of a brief introduction to what the City Intelligence Lab, where we're all, as you see, we all have like the same background. So we are shamelessly promoting what we are doing, which is actually what this workshop is also relevant to. And we will show a little bit of that. Don't worry, we're not going to be like showing that for 4 hours every day from now till Friday. This is the last time you will see it. But it's good to have a bit of a context on, you know, what we're all doing and why we're like interested in this. And yeah, is this okay for everyone? Can you just say it's all good? All right, so I'll present my screen. I think the first thing you will see will be my horrible background, my horrible desktop background, which needs to be kind of like cleaned, but that's not to be discussed right now. So let's look at that. Sorry, wait. View, present, slideshow. Interesting. Why can't I present just here? Okay, sorry, I was presenting already. So what is the City Intelligence Lab and what we are doing? So first of all, we are part of the Austrian Institute of Technology, because you might have never heard about this before, but it's actually really large in Austria. I hope the Austrian people, at least I saw a couple of people are here from Austria, they have heard about it, but if you haven't, this is who we are. These are some like simple graphs that show what we are. We are an Institute of Technology, we're not a university, so the little thing here says like, we are the largest non-university research institute in Austria, which means we're not really a university. We're not teaching. We're like doing research, which is project driven and funded also, but it's not like an academic institution. Exactly. So we are mainly owned by the Republic of Austria, for like we're a public institution, and also the Federation of Austria Industry. So like we are essentially funded by the industry and the state, which is a great thing because we need to be, you know, doing both. So what we do needs to be relevant to the industry as well. Very quickly, this is kind of like our structure. We're doing projects all around the world, and we are part of the City Intelligence Lab is part of a unit called Digital Resilient Cities, which does a lot of other things other than, you know, what we are doing. And need to a little bit like give a context of that. So doing projects all around the world, mostly about urban transformation and resilience. So smart cities, energy and resource management, a lot of that, actually waste management and everything related to urban resilience, like, you know, water, pollution, resources, all of these. This comes more a little bit to what we are doing within the unit. There's two like research fields. So say like one is like urban resilience, the other is like smart spatial planning, which is what we are mostly like affiliated to. So the smart spatial planning part does a lot of like urban analysis and simulation, computational urban design. We're slowly going deeper into what the lab is doing, interactive interfaces, mixed reality, And this is what the lab looks like when we're all pretending to be looking at the model, very interested, and we're taking pictures of. But this is the space. There's an actual space. The lab is a lab. It's an actual physical space, but it's also, very importantly, the part behind it is like the research. So we are a kind of like internally funded research project, which is called Cognitive Urban Design Computing, led by Professor Reinhard Koenig Professor in Bauhaus, and its goal is to somehow like try to understand this interaction between computation, algorithmic, whatever you call that, like urban planning and kind of like the user. Like, how do we actually make sense of this and use these algorithmic processes? So this is what the team looks like. We just added one more member. We have two more members that are coming next week. So Reinhard Koenig and myself leading the codec and the CIL, and Theodore Galanos is a person who we started working with from the beginning. I've only been here in the AIT for the past like year and a half. Before that, I've spent time in IAC teaching and trying to get a PhD, and also London at Foster's and UCL. But like I joined here like a year and a half ago, and the moment we joined, like Theodore started working with us, so it's like we can say Theodore, our AI expert in the group, has been working a lot with us since the beginning. Narid and Yosha are PhD researchers, and they've been working with us for less amount of time, but they've produced incredible amounts of work, and really would like to praise their work. And Dielza as well. They all started together like beginning of this year almost, and we've together like built like some really cool tools that I'm going to show in a bit. And we have now Magdalena, who is one of our interns, and we have two more interns. If you're at any point interested in collaborating with us, Mohammed raised his hand, so if someone can kind of like bring him up to the panel, I think he's one of our participants. So if anyone is interested to work with us, like, collaborate or whatever, like, please, this is also a reason why we're doing this. We want to meet new people and, like, collaborate, do interesting work. I already know with a couple of you that we're talking already about collaborations. So please feel free to, suggest things. I'm going to skip that's kind of like what we're trying to do, like kind of like bring together all the different performance aspects of urban planning in a kind of like workflow. You probably know this or have seen this before, Decoding Spaces. So the codec group has been actively involved in like developing Decoding Spaces. So that's part of what we've been doing. That's a little bit before I joined, but like it's really a big important part of what the lab has been also involved in. In case you don't know it, it's a great spatial analysis and a spatial like generative computational design kind of like a tool for Grasshopper, and you can do a lot of things like metrics of the space, such as like the closeness and betweenness and like centrality and all of the space index, like typical measures and like closest path you can generate. I'm not going to talk much about Decoding Spaces because if you've seen it before, you know it. If you haven't seen it, you can very easily go to it. Yeah, like you can generate streets, you can generate like typologies, you can very quickly kind of like use that to create like parametric models. I hate that term, but yeah, that's what it is. And design whole like neighborhoods very fast and very quickly, kind of like play with parameters. We will see something similar, but not exactly that today. And that's one of the things that we've done. I'm not going to spend so much time there. We've done a lot of like tools for like accessibility. For example, this is accessibility of transportation, and Yosha will be talking a little bit about that because it's his kind of like expertise as well a little bit. In this case, we see how like you can design in a city like a tool where you can see what you can reach within a certain amount of time by placing a point in the city, or by kind of like selecting different transport modes and seeing, essentially seeing the accessibility of transportation and walking in the city. Skipping that, a lot of like simulations such as like rain simulation. This is rainfall of simulation. Like you have a particle system and you like trying to measure how much water like goes through the city with a digital terrain model, and then find areas that are like, you know, more dangerous for flooding, and then, you know, kind of like identifying them and, you know, creating mitigation strategies and whatever. That's all kind of like a context of our work. What we mainly work right now on is our infrared, let's say, framework. We can call it framework, intelligent framework for resilient design. It's what we call it. It's a cool name, and we thought it makes sense. So what is infrared is not, it's not like really one tool or one kind of like, you know, software or something like that. It's like a group of processes and tools which are essentially trying to use machine learning to predict performance, urban performance, or to like assist. Mainly, that's the best way to describe it. Assist the designer in designing with performance in mind. So this is very much relevant to what we see today. This is like, for me, my favorite picture, because it shows why we can't understand, you know, why we can predict quite well, like, you know, performance. So one of these is a solar radiation simulation. The other is a machine learning prediction. And they look so similar that we can't even tell the difference sometimes. And that's kind of like what we've based a little bit the work of infrared on. It's like we're training a lot of machine learning models to predict simulations that would normally take a lot of time to do so. So in this case, this is solar radiation. So what we've done is taken the whole city of Vienna, chopped it off in parts. It's actually chopped off already from the government, and take all the models and pass them in kind of like through solar radiation simulation pipeline, created thousands of simulation kind of like results, and then train a neural network to predict the simulation. And this is what we see here. So you see like input, and then this is the simulated result, and this is the predicted result. And we see how well the model performs in both large scale and kind of like detailed scale of the city. So we did the same for, like, solar radiation is kind of like relatively easy. It's not that cost effective in terms of computation, but CFD is kind of like more groundbreaking part of this tool, because it takes really longer, and it's, you know, it's one of these simulations can take up to 3 or 5 hours to do, so you don't really have the time to run them. And again, we trained neural networks to predict, and we can see here the results of like a very early stage model. We have better models, and then we kind of like implemented that in an actual kind of like parametric interface. So essentially what we see here is like someone changing parameters in the model and immediately seeing the microclimate statistics or microclimate performance of that model, which is something that is a bit of a breakthrough, because you can actually design with you know, with thermal comfort. And we've created a website. In case you have not seen that before, I would ask someone to send the link to the infrared, maybe Narid, who has actually set up all of this. Can you send a link to the page? And we've made this accessible to everybody, so that, you know, you can actually just select a location and go there using OpenStreetMaps. You can find, you know, your area, and you can very quickly kind of like see that in action. I'm gonna actually show you very briefly how that works by bringing a page. Can you all see that? Yeah.
Yes.
Cool. So yeah, it's not like working perfectly, but you get the point. So here is, I go here, for example, I'm in Vienna. I don't need to go somewhere else. And this is kind of like the Vienna International Center. And I can see here that I can see 2D or 3D, and I can select, for example, a certain wind direction, and I can predict the wind factors of that wind direction. And hopefully we're not going to crash the server, Narid, by all trying it.
Fingers crossed.
Fingers crossed. So I just clicked predict, and you can see, like, in a very short amount of time, you get a CFD, an actual proper CFD result of that. Or you can do a wind comfort snapshot, which actually makes a little bit more sense, because it actually shows you areas that are dangerous, or areas that are like more comfortable. So using the Lawson's criteria in wind comfort, in case you've been kind of like you're familiar with them. So you see here, yeah, we just click a button, we can get like something that would normally take hours to run. And that's how we advocate that machine learning is actually very beneficial for you know, urban for resilient like urban planning, so to say. I'm going to continue here. Yeah, we've done the same. We've implemented the same model in Giraffe. If you haven't heard of Giraffe, it's a very interesting tool done by our Aussie kind of like colleagues. Go Australia, now he's from Australia, he's happy. And we've implemented like our models in there. And like actually recently, like a few days ago, Giraffe announced that you can actually purchase kind of like the tool to like, or credits to work in the tool. So it's all already up there. And there's a lot of interest for that too. So we are really happy. If you want to work with this and you want our help, please let us know. We're very happy to collaborate with you. Again, that's one of the reasons we're doing these workshops. So we've also implemented that in, of course, Grasshopper with specific kind of like tools in Grasshopper, but that's kind of like showing infrareds, also other like capabilities, such as like looking at, you know, as I said before, accessibility and other simulations such as noise or wind or rain. And here we see how actually within Grasshopper we design with infrared again. We're moving a park around in an area, and you see immediately how your wind profile changes and how the position of the park or the layout of the buildings around you affect the performance of the design, which is again I mean, I've been working with CFD and wind simulations and integration of simulations for more than 10 years now, especially CFD. And this is it was like a dream for me to achieve that. So I'm really, really happy with what we've done. But me praising our own work doesn't make much sense. Here is how we can use the same tool in a generative way. And again, this is something we can think about doing in this workshop. So not just looking at iteratively changing things, but running a whole bunch of like a whole design space and and understanding whole performance space. So you set some parameters. This is a bit of a kind of like a mashup video, but you get the point. So you can set a set of parameters and like explore a big solution space, and then you can put some fancy glasses on and make it look nice. But I think you get the point, right? You've seen some of this before, and if you haven't, I'll be very happy to show you more. So of course, it's all part of the lab and integrated in our, like, we have big interactive interfaces and AR models and all those other kind of like, that's why we also in your questionnaire you have like also interactive design systems, because they're like big part of what we do. And we were talking with another workshop with Hologram with Guillaume to see if we can connect the two workshops and see if we can kind of like present something interactively. This is our website. Again, I don't know if you can send it to the chat, Narid or someone. If you can send the website of the CIL so that you can go there and see like if there's more projects and more interesting stuff. So thank you very much from my side. And yeah, any questions and any kind of like comments and any kind of like requests, please. Are you all sleeping already?
So can you hear me?
Yes.
Yep.
So I think I've read somewhere that you guys used Vienna, the city, to train your machine learning algorithms. So I have two doubts regarding that. Why Vienna, and why the scale of the set of buildings you use to train, to make simulations out of, and use that as a data set to train your algorithms? Why that scale? Why that place?
It's interesting. Yeah. First of all, to clarify, we started off building machine learning models for Vienna because we were designing a kind of like a performative urban design tool for Vienna. But that's not the case anymore. This is what I showed. This is like what we used to train the first model. We've used for the CFD, we've used 5 or 6 different cities.
Okay.
Completely different cities like Sydney or Vegas, or like completely different like scales and and typologies to train the CFD, because there's difference between different models. So for example, the wind model that we've produced is a kind of like global model, so you can use it anywhere in the world. But the solar radiation models are specific because they depend on the
latitude,
meteorological kind of like specificities of each city. So each city has a different typical meteorological year. You can't be basing a kind of like a solar radiation model on others. And the same for thermal comfort. You can also, there's different ways, but anyway, it depends on the performance metric. Yeah.
Okay.
Is that answering the question?
Yeah, and why the scale of those, the area in which we can see those
the scale. Okay,
maps.
so again, very good one. The scale that you see here is, first of all, the one that you see in the website is a restriction of the computation. We can do larger patches, but we want to not crash our service.
Okay.
It's like the openly available tool. In our tools, we also have bigger.
Yeah, but the simulations, they were carried out with a scale similar to those areas we see in
We've
video.
done, again, simulations in more than one scale.
Okay.
So it's not just that. Like, so
okay.
We are like looking at, 250 meters or like 500 meters or like 1 kilometer scale. So the scale has to relate to the urban planning. So we're not interested in like single building simulations right now. More like the scale of a couple of 4 building blocks, sort of say. That's kind of, because that's the scale that we work on. I haven't shown projects that we're working on, but that's kind of like the scale of the projects we work on.
Okay. And I asked that because, wind, it tends to behave in a certain way depending on context, right? So it really makes you go further than just building your
having worked with wind a lot, like I completely understand your concerns, and there is a difference between going like, you never do like a whole city like so you will include like a certain like proximity when you do a simulation. So that's what we're also trying to do. Again, an important point, this is aimed at preliminary studies. Like, you're not going to do that. You're not going to use that simulation to validate, okay, this is my amazing courtyard, naturally ventilated, I've tested it with a machine learning CFD. No, because that's not the case. But when you're designing a courtyard, you have no idea what the wind does. You need some sort of like guidance, and that's guidance is what we're trying to guidance and accessibility of simulation, which is something. Yeah.
Thank you.
Questions? Thank you, Andrew. These are great questions, by the way.
What do you see as the next evolution of, your research?
Yeah, I think that part of that, but like that. Well, democratization and accessibility of the tools is what we really want to be looking at. So the idea is there's this big problem, the way I see it, at least, and I don't know, Nari, Dilsa and Joshua, correct me if you have a different view, but the problem that we have is we have like all these like I would give this presentation normally. I would show like I don't know if you guys have seen or remember GC, like generative components. Like at some point we had generative components, and someone, Gustav de Biswas, managed to connect it to Ecotech, and that was like the breakthrough. Like someone managed to connect like Ecotech to GC and managed to see one solar radiation simulation. That was like 12, 15 years ago. Now we have so many tools and so much capability of like connecting performance to design, but we don't really understand it still. Like, we're not making sense. So our goal is to try to distill, instead of like showing people like performance maps, to give them actual guidance, to give them actual advice on how to design. And that's where we're taking our AI machine learning to, like, trying to enable the designer to understand what he's doing, not just by like running 1,000 options just for the sake of running 1,000 options and then say, look, we run 1,000 options, but we've manually created the last one because that's how architecture works. It's like, you need to be able to design and at the same time get feedback about what you're doing. This is wrong. You have a very tall building next to a, you know, plaza. You're gonna kill everybody that, you know, that works around because you're in Norway.
I would have a question on the, so you trained the model with an existing building, so from the existing building structure, isn't it? So like for the wind simulation.
We also have parametric, so we're training it with also like parametric models of you know, non-existing.
Yeah, but did you investigate if you take like the same plot and just replace like the typology completely, like say you have a dense courtyard structure you ran the simulation on, and then you put a high-rise there and get rid of the courtyards? How does the prediction, is there, did you do any testing? How well does it predict? Still predict, or is it linked to the initial typology in terms of results? And
that's exactly where we have enough variation in the models in the training that we can have very different. That's why we have diverse geometries, such as like, you know, something like Sydney downtown or Sydney kind of like sprawl, like very different like typologies, and the model reacts, as we've seen up to now, relatively well in accuracy. So we've tested its accuracy and it like works quite well up to now.
Okay, cool.
But yeah, it's a very good question, and these are like excellent questions that will relate to what you will produce within these 4 days, which is, you know, again, you will see while you're producing similar methodologies, you know, how do you test? And there's ways, how do you test your models and their accuracy, and, you know. Now, do you want to say something? You've unmuted your microphone, or you don't? I thought you wanted.
No, not at all.
Okay.
I mean, like a little, like look behind the curtain. There has been a push internally of validating our models, not just saying, you know, yeah, it feels good, and like our internal experts see that it appears to be quite accurate. And yeah, so going through empirical tests, making sure. But with that, we've also been experimenting with what kind of data we're using to train it. The variations of if we do just specific cities, or if we do a combination of real world data and cities, as well as a parametric. What about them on its own? But yeah, that is in the works as we speak.
More questions? I'm sure there are more questions, or we can move on and start talking about what you will be doing. Yeah. Should we move on? Okay. Always here to answer more questions or to see how we can, like, you know, investigate these questions together. So I will now ask Nari to continue by showing by giving a short introduction on AI. I want to say a few things before you start. Do we have a slide before, or is it starting directly there? Yeah.
I was going to start, but feel free to go ahead.
But I just want to say one thing. Just wanted to put it out there. Like when we're talking about artificial intelligence, there is, you know, there's different understandings of the term, and when we're talking about artificial intelligence, most people today are talking about machine learning, but artificial intelligence is much more than machine learning. Thank you very much. This course is more about machine learning than artificial intelligence in general, because you've been using a lot of artificial intelligence concepts, all of us, and we've been using them already. Like genetic algorithms, for example, are artificial intelligence as well, and you've been using, you know, Galapagos or other kind of like generative tools that are as well artificial intelligence, or cellular automata, again part of the artificial intelligence research. So artificial intelligence is not new, and it did not start with Google, and it's not like it didn't start with Deep Dream. I just want to say that deep learning is what came up recently, and it is here because of the availability of data and the availability of GPU computing, and that's the main reasons why we're talking so much about artificial intelligence lately. But it's something that exists decades, and you know, you probably all know that already. So I just wanted to be, you know, feel better with myself by saying that before we go into the machine learning part. But please, now take over, and yeah.
Thanks, Angelos. I couldn't have put that better myself. So as Angela said, this here will be your introduction to AI, but less so AI and more so machine learning. But before we start, before the workshop, we asked you guys to complete a form asking about your skills and your interests. Now, one of the questions we asked you was how proficient you were with artificial intelligence concepts. Now, it was great to see such a wide spectrum of responses, and it was even more amazing to see that one of you placed yourself at a 9, another 2 at an 8, borderline experts. Now, to be completely honest, to be completely candid, I kind of placed myself at about a 7 or an 8. So, you know, throughout this talk and throughout this entire workshop, if anyone feels that I or my colleagues have maybe misrepresented or maybe not conveyed as effectively as we could any information, please speak up, raise your hand, you know. This is not just a learning experience for you guys, but, you know, for us as well. Another thing I'd like to make clear is that this workshop will not make you a 9. In fact, the focus of this is less about giving you the theoretical underpinnings of machine learning or artificial intelligence, and more so about showing you very practical, very hands-on examples and workflows that you can pick up, use right out of the box, and then apply to your own problems. You might not know everything that is happening inside the algorithm or even inside the code or scripts. If you do, kudos to you. But we'll be providing you with enough direction that you'll be able to tweak this work and sufficiently apply it uniquely. Now, with that out of the way, let's start with some definitions. And I'm gonna need some interaction here, yeah? So let's establish a baseline. Could someone who identified themselves in this question as a 4 or below take a stab at defining machine learning? Now, even if you know nothing technical about machine learning, it's so in the zeitgeist that you must have been exposed to the term through media, through research papers, or through its like wide applications in the world. So, a 4 or below, would anyone like to define machine learning? There is no wrong or right answer here. Okay.
I'm gonna try and take a stab.
Brilliant, thanks, Sanjay.
Yeah, so the way I understand it is when you leverage computational power to identify patterns from a large data set, and you kind of guide it around what kind of patterns you're looking for, that's what I would think machine learning would be.
Sure. So in essence, there's 2 bits here, data set and trying to grab a pattern from that data set, yeah? Right. Would anyone else have any other maybe alternative perspectives or maybe other layers to how they see machine learning? This is open, you don't need to be a 4 or below. Nor am I looking for a Wikipedia definition.
Okay, maybe I can try one.
Go ahead, Edward.
So like training a model with a known set of outcomes so that in the end, what you get from is to just put in something unknown to the model and still get a usable outcome. So that's how would I say, high level.
Yeah, no, absolutely. So there's a lot of different interpretations of machine learning. There might be some hard definition out there, but I like this idea of interpretation better. My favorite interpretation comes from this bloke here. His name is Pedro Domingos, a professor and a machine learning expert, and someone we'll talk a bit more about later on. The way he defines machine learning is that machine learning is the scientific method, but on steroids. He says that it follows the same process of generating, testing, and discarding or refining hypotheses. But while the human scientists might spend their whole life coming up with maybe a few hundred hypotheses, machine learning can do this in a fraction of a second. In other words, machine learning automates discovery. Now, when we talk about the schools of machine learning, there are often these lines that we draw to kind of understand it a bit deeper. There are 3 main ones, which is sometimes 4, and at other times 14. But let's start with the 3 main schools, the most widely accepted definitions. And as much as I hate to say it, the Wikipedia definitions kind of go off. So supervised learning. Supervised learning is a way to learn a function that maps an input to an output based on examples. And I think the best way to wrap your head around this is by example. So with that, let's talk a bit about cricket. For those who don't know, cricket is a sport that involves hitting a ball with a bat, among other things, but let's not talk about it. Let's say we want to use a supervised learning approach to train a batsman, where the input is how the ball is coming at you, the delivery, and the output is what motions are required to successfully hit the ball. As per the definition of supervised learning, the approach requires examples of input and output. So these examples in this training a batsman approach could take the form of watching a really good batsman, I don't know, let's say Don Bradman here, play. Over time, I should be able to pick up some patterns in his behavior. I should be able to see, okay, if a ball comes at Don this way, he hits it like this. If in another way, he changes his approach. And maybe over time, I'm able to pick up this correlation between input and output. This is supervised learning. Again, I just want to draw attention. If anyone ever has any questions, any concerns, if you didn't understand something, just shout. Happy to address. So unsupervised learning, again, the Wikipedia definition, looks for undetected patterns in data sets with no labels. But you might ask, what is this no labels? What is a label? Well, going back to the cricket example, imagine we didn't have the ability to watch past legends play. If we didn't have any data on how the batter reacted to the delivery, and we only had our data on the balls being bowled to us. Labels are the corresponding output to each input. The batting motion to each delivery. But we still want to train a batsman to handle batting back a delivery. And since we don't have labels, since we don't have how Don Bradman hits the balls, one approach is through unsupervised learning. Perhaps the first step to hitting a ball is to recognize what type of delivery it is. Is it a leg spin? Is it an off spin? Is it a fastball, or one of the few dozen other types of deliveries? And this is perfect for unsupervised learning because it takes the data about all the different deliveries and tries to find some patterns, maybe group them, maybe represent them in another way. Understanding. And finally, reinforcement learning. Reinforcement learning is used to train agents to take actions in an environment to maximize some idea of reward. And going back to our cricket example, the agent in this definition would be the cricket player we want to train, the batsman. And again, in the scenario, we don't have any data about the previous batsman. We don't have Don Bradman here and how he hits the cricket ball. But also, we don't have a pre-existing data set containing all the different ways balls are bowled to the batter. We have no data. So for reinforcement learning to work in this example, the batsman we want to train must be put in a simulation environment where balls are delivered to the batsman. And with minimal to no knowledge, the batsman must try and hit the ball. Now you might think with no knowledge, we can expect the batsman to be terrible. In fact, we could expect a lot of flailing and unintelligent movement. But one of these times, just maybe the batsman might unintentionally connect with the ball. And this is what we want. But how do we reinforce this behavior? Well, with a reward. When the agent happens upon something that we as the trainers want them to do, we give them some sort of reward. And over time, the agent will adjust its behavior in a way to maximize that reward. Now, that was a lot of information there. Does anyone have any questions at this point? Okay, good. So with all of these Wikipedia definitions and within the articles, they always comes with a section called algorithms or approaches. They list a series of machine learning algorithms that can be used for each of these schools. However, some of these algorithms can exist in 2 and even 3 schools. Take the artificial neural network. The most common use of the neural net is supervised, where you provide the network with both inputs and outputs, the input and output pair, mapping those two, and you ask the learning algorithm to find patterns and correlations between these inputs and outputs. And that's why it's considered supervised, mapping input and output. However, there's a variation of the neural net that makes it fall under the unsupervised category. For instance, if you tell the algorithm that the output is actually the same as the input, this becomes unsupervised. This is considered unsupervised because, as per the definition, it looks for previously undetected patterns in a dataset with no pre-existing labels. This is known as the autoencoder. Self-organizing maps, Boltzmann machines are also variations of neural networks in the unsupervised category. Now, this can be taken a step further. The neural network can also be used in reinforcement learning. If you use the neural net to allow an agent to make decisions in an environment, and the environmental feedback determines if the action taken is good or bad, this becomes reinforcement learning. And this specific algorithm is known as deep Q learning. So with the highlighted algorithms, neural networks, Boltzmann's machines, self-organizing maps, autoencoders, deep Q learning, and all the variations of the same idea. Now we've gotten to a stage where if you're a beginner at machine learning, and if you're not overwhelmed, I'm impressed. With all of these kind of blurred lines of the schools, but then also the algorithms and how algorithms can exist in different schools, and the verbose definitions of all the different schools, and then trying to wrap your head around this overarching ontology can be a bit tricky at first. When I was first learning machine learning, I found it helpful to think about it in this way. Supervised learning is all about finding correlation between input and output. You see an example of input and output, you try and find patterns. Unsupervised learning is all about discovering patterns between different inputs, where you don't have an output, where you don't have labels. And finally, reinforcement learning is about developing a certain behavior. So, with all these different definitions in mind, let's do a little bit of an exercise here. I'm going to say a couple of problems, specifically within the built environment, where I know that I'd like to use machine learning, but I don't know where to look. I'll state the problem, and you have to give me a direction as to where to start looking by saying one of the three schools and why. I think we'll do this with a poll, or shall we actually point? Can you guys actually annotate on your screen? Does everyone have that capabilities?
I don't think.
No.
Was that a yes or a no? Because I can see Dielza, I can see Yosha.
Someone annotates already.
How are you doing this?
So within Zoom, there should be the ability to click annotate.
Yeah, if you you say on top, you see like a little green thing says you are viewing Narit King's screen. Next to that, there's view options. If you click on that, there should be somewhere which says annotate. Do you have that option?
Yeah.
Lovely. So
then please use the arrow. Annotate with this arrow tool, because then we see your name and it's a pointy thing.
So you can just annotate and then click.
Wonderful. Great. So I'll read through the question together, and I'd like you to, oh my word, thank you, to stick your pointer as to which of the three schools of machine learning you think it is. So first problem, I have a data set where each building in a city is a data point. And for each of those data points, there is information such as building height, GFA, the architect that designed it, the building use, the cost of building, so on and so on and so on. My objective is to find similar buildings to one specific building. So I have an input building that I have a particular interest for some reason, and I want to find some other buildings in that data set that are the most similar. So which school of machine learning should I use? Everyone use your annotate tool and put your pointers inside inside.
Can I ask again, everyone to like use, if you go to annotate, there is a little thing like this mouse, text, draw, stamp, arrow. That arrow thing has your name as well. That instead, but you can also, yeah, of course, use just an arrow, like, but the arrow thing has your name.
It doesn't persist between everyone. I think it hops around when people click.
I'm not sure. Do you see mine? Because I'm clicking, but it doesn't give me any response.
It's possible that it is slow.
Okay.
Let's clear all drawings and start again.
Maybe we leaned in too hard to play with all the tools of Zoom, hey?
Yeah.
That's on me.
It's fine.
I'm seeing a lot of supervised learning, seeing a little bit of unsupervised. No one going for reinforcement, totally fine.
I'm clicking, but it's not accurate.
Nah.
Don't worry about it too much.
Yeah, it's all good. Let's go through it. So someone from the supervised learning camp, can you explain to me why you think supervised learning is the way to go?
Because that's I think that's like this high level definition I was stating before.
Right.
So you have an existing data stock, so to say. You train the model, and then you give it like new data which it hasn't seen before, but it just tries to figure out if those match the criteria or not.
Sure.
So
totally viable. Would someone from unsupervised learning tell me why they think that?
Could be also an autoencoder, like just feed them all the data and let them generate something based on the data, just encoding the numbers.
Absolutely. I think someone's a bit more technical there, Zvonko. Someone has done their machine learning. But yeah, I would agree. This also could be an unsupervised learning problem. In fact, you could use any school to solve this problem. There's no specific approach that you need to shoehorn yourself into. Some might have benefits over the other, but don't feel restricted to thinking that it must fall under one of these three schools. Let's do another. Let's clear the screen as well. Thank you. So number 2, I want to give control of a smart building to an algorithm so that it can intelligently control the air conditioning and the windows. That said, I will still allow the occupants of the building to take control and go against the algorithm if they see fit. I don't have any data, but will place sensors around to collect data over time, and also record the actions of occupants in relation to the sensed data. Which school of machine learning should I use? A lot for reinforcement, a little bit for unsupervised. Okay, interesting. Angelos, I saw your pointer. You pointed to unsupervised learning. Tell me, why do you think it's unsupervised learning?
So I'm just trying to demonstrate here.
Oh, sure.
That you can do most of these problems with any of the approaches. And I think that we've had this chat before, but I'm just trying to demonstrate that this is not very exclusive. It's also it's also possible to do things in different ways. It's just a matter of setting up the right workflows. That's what I was trying to demonstrate.
Absolutely. And I think, be that as it may, you can use any of these approaches. Some are a bit more suitable than others, and often you'll find that what restricts you is your data. So notice in the problem, we say we currently don't have any data. And that jumps out to me immediately that maybe reinforcement learning, where you throw an agent into environment to kind of test it out, might be the approach. You don't need any pre-existing data about it. Then you've got to think, the issue is, then how do you give it a reward? It's a complexity we can think about. But the point here is that often data is the limiting factor into which algorithm and which approach you should use here. Can we clear the screen, please? One last one, this will be super quick, we'll pump through this. So the last problem is, I want to measure the occupancy of an office bathroom, as well as make sure that there is no graffiti and other illicit activities happening in a place of privacy. Now, I want to use camera footage and image recognition to classify what the user is doing inside the store. So which school of machine learning should I use? Okay. Would anyone like to speak about their answer? Just one person giving a reason why? I might pick one of you out of the group.
Can you hear me?
Yes, Stefan, go ahead, please.
Well, I have chosen supervised learning. My opinion is that we can approach this problem with neural networks, and we have to train the network to understand that the person on this image is doing an illegal graffiti, and the person on this image is not doing an illegal graffiti. So I think that there should be some database, and this should be a supervised learning.
Sure. Very interesting that you say that there should be a database. In this exact example, a database of what people are doing inside the stalls of a bathroom? Sure, that might exist, but did anyone else have bad vibes about this problem, you know? I mean, installing cameras in bathroom stalls, I wouldn't want someone watching me doing what I do in there. So yes, you could get the results that you want if you applied supervised learning. You know, there might be a data set out there that exists, God forbid. But just because you can apply machine learning doesn't mean that you should. And I think this is an important point that I want to instill here. This course, yes, aims to give you practical and hands-on experience with machine learning, but also equip you with the ability to understand when and if you should apply it. Now, machine learning is very much in the zeitgeist, and it's being applied in almost all facets of our lives, but maybe we shouldn't blindly follow this trend. With the benefits of machine learning comes a few downsides, and a little later we'll talk about these downsides. But for the future, whenever you're thinking about applying machine learning, I want you to ask the following questions. Number one, do you really need machine learning? Number two, can this problem be solved another way? If you can clear the screen, thank you. So I mentioned Pedro Domingos, the gentleman who gave a lovely interpretation of machine learning that I picked on. He has his own ways of slicing up the different aspects of machine learning. He calls it the 5 tribes. Although just being conscious of time and to get to you guys in your groups and doing the work of the workshop, I think I might skip this. Happy to chat about it a bit later, of course. So you guys might have heard of something called deep learning. Now, this time I'd like to hear someone on the other side of the graph, the 5s and above. Someone who has said that they are fairly knowledgeable about AI. Because I have a written definition here, but we'll get to that in a bit. But I also want to know how you guys interpret it. So, how does deep learning differ from machine learning? Can I get a response here? I might pick out the 9 soon.
Well, maybe I can give an answer.
Addison, please.
Well, I think as a neural network, it has many hidden layers, but in deep learning, you have a lot of them. So the network becomes very, deep, and abstractions become more meaningful through this structure.
Okay. So you're saying that deep learning is pointing specifically to a type of algorithm, the neural net, and a specific subtype of that algorithm, something that has a lot of hidden layers, as you said.
Well, it might not be that specific, but I think the example I gave might be one of the examples that might illustrate that concept.
Yeah,
but I'm
absolutely.
not really sure.
No, I think you've touched on something there. So like going back to how we've defined machine learning, we've defined it not with the algorithms they use, but with the ideas behind it and the problems that each school solves.
Sure.
Deep learning, on the other hand, is defined purely by the algorithms. And as such, deep learning doesn't fall neatly into one of the three schools, but is yet another way to slice up machine learning. The algorithms that deep learning are based on are what's thought to be the building block of the biological brain, that is the neuron. And this started in 1943, where the initial models from neural science, spearheaded by Warren McCulloch and Walter Pitts, thought about how to model the biological neural networks mathematically. From 1957 to 62, Frank Rosenblatt created a single layer and multi-layer perceptrons. This was the early computational model of the neuron. In the 70s, the algorithm used to train the perceptrons, also known as backpropagation, was developed. Now, this makes a few steps away from biology, but alongside that sprung up an algorithmic variation of the neural network, known as the recurrent neural network, which can handle time series data. The recurrent neural net is still the backbone for a lot of natural language processing models today. In the 80s, we saw convolutional neural networks, which is still used for deep learning with images and spatial data. Convolutional neural networks will be a bit of a focus actually for us in the workshop. And alongside that was the creation of the long short-term memory, or LSTM, a further variation of the recurrent neural net. In 2006, this was arguably the birth of deep learning and the deep learning revolution. Now, this saw like a coalescence of a really big data sets with big boy computational power and a long history, as we've seen, of brilliant algorithms. In 2009, we saw ImageNet and AlexNet. The seminal moment that really like pushed, that really motivated, that captured the AI community and really showed the capabilities of neural networks when applied specifically to images. In 2014, we saw the development and popularization of the Generative Adversarial Network, or GAN, a highly successful method to teach machines to generate rather than discriminate. And again, we'll be touching on this in the workshop. In 2016 and 17, reinforcement learning became a household phrase as AlphaGo defeated Lee Sedol in the board game Go, something unaccomplishable by brute force methods. And again, reinforcement learning, something we'll touch on in this lecture. Most recently, the transformers. Transformers and BERT, the bidirectional encoder representations from transformers. These algorithms are brilliant at natural language processing, but also poses ethical questions, you know, in this post-truth world. You know, it's a side note here, but I find it super funny that this algorithm is acronym. The acronym of this algorithm is BERT, and the state-of-the-art algorithm before this one was called Embedding from Language Models, which shortened to ELMO. Now, throughout this timeline, I mentioned a few key deep learning algorithms, such as the convolutional neural network and the recurrent neural network. And this next section will talk about how deep learning has been used specifically within the built environment. So these three here are reports from McKinsey, and they highlight a common perception of the architectural, engineering, and construction industry, and that is their sluggishness to adopt new technology. We can see here that the reports from, I believe, 2016, 17, and 18 show the construction industry to be one of the slowest industries for the uptake of new technology. This isn't just AI, but it's any new technology. In 2019, a paper by Tanya Papasoteriou tried to gain an understanding of machine learning specifically within the AEC. You know, we have this perception that we're slow to adopt this new technology, but you know, Tanya really tried to capture where the AEC was. There are a few conclusions that she drew. Number one, there was this exponential increase in the number of publications in the field since the early 2000s. And this is not just common to the AEC, but for any field there as well. She points out that there is certainly no indication of saturation of a particular field. She also does steganography, which found the 7 main clusters or inventories, as she would say, that describes how machine learning has been applied. She states that the breadth of the clusters is indicative of the interdisciplinary nature of the topic, which spans across all fields of architecture. It's interesting to note that the education cluster is a dominant one, and it's indicative of the momentum behind machine learning in the AEC. A couple other examples. So this project here is a project by Alan Wang. His objective was to take point cloud data of construction sites from LiDAR scans and do clash detection with existing models. The issue previously was someone would have to go onto site and visually inspect if a component should be where it should be, if a component is where it should be. With this method, a non-expert can go on site, shoot a LiDAR scanner around, and the machine learning behind this, the point net architecture, will be able to take all these points, group them as to what component they are on the construction site, and then also have the spatial positioning of it. As mentioned, this here was the point net architecture. This is known as a version of 3D semantic segmentation. So what was interesting was he developed a parametric model to generate the training data set. Yet when he took his trained model, something that was said to perform 99% accurate on the training data set, and he applied it to a real world, a noisy data set, it struggled, quite obviously. It seems that the roof and the floors and the walls were correctly identified, but it really wasn't able to capture anything of more detail. The next application of machine learning in a built environment is by Lachlan Brown. His goal was to try and solve the problem on the screen here, incompatible representations of architectural models. And he asks the question, what if there was a way to infer BIM data from data poor representations? Data poor representations being things like architectural drawings, hand drawings. His first task was to automate the definition of the room elements into the floor plans. He took an approach known as the mask RCNN, something we'll be having a play with a little bit later. Mask RCNNs are a type of instance segmentation, where not only the types of objects are found and are highlighted, but also when and where new objects start and stop. In other words, it's able to distinguish between cars rather than having a giant blob of pixels that all say car. The issue and the problem here was that he didn't have the data in the available format with all these rooms labeled. And for this, he had to label his own data set. And that was incredibly time consuming. By the end of it, he labeled 454 floor plans and through this web app here. By the end of it, the results were decent. You can see here that the rooms were successfully distinguished and some even labeled quite correctly. But if you saw a little bit, if you tested it on plans that were a little bit more unique, it really struggled. For instance, it wasn't able to understand plans on a diagonal. There are some other projects here that I know of, but I don't have any media about. For instance, using a camera attached to a robot to traverse concrete tunnels to check for cracks. This is a way of image detection, essentially. Another is predicting the use of bike sharing schemes and times for load, so that the companies can shift bikes around to deal with all these differences in load, and so on and so forth. You guys can see this. You'll have the presentation. Now, I know I've been talking a lot, so there's just one last thing that I want to touch on before we get to the break, and it's that it was last year, 2019, that it really became cool to kind of point out the limitations of deep learning. You know, books such as Hello World, Being Human in the Age of Algorithms, you know, Rebooting AI, they really kind of rationalized the mysterious shroud that is AI and presented it to, you know, the general audience. You know, that even though there's a lot of machine learning success, even though there has been a lot of wins, it's still so far away from being able to do so many things, you know, such as common sense reasoning, you know, building knowledge bases and a bunch of other things. The point here is that ultimately deep learning is not a silver bullet. And further, even the deep learning algorithms, in fact, all algorithms for that matter, come with their own, you know, idiosyncrasies, their own biases, and you know, their own drawbacks. And this is a problem. One that's most of the time hidden, because so much of our world is controlled by these algorithms. And as such, we've grown our own biases, this overly trusting attitude towards the computer. You know, a great quote by Hannah Fry is, just because a computer says something doesn't make it so. Meredith Broussard calls this behavior techno-chauvinism. In 2016, ProPublica published an investigation of an algorithm that would provide judges with a numerical likelihood that a criminal would recommit a crime. The algorithm was called Compass, and it was used to help real judges in real US states to help sentence these criminals. The investigation by ProPublica revealed that whatever the algorithm Compass was used, which is closed source to this day, was simply put racist. In the past, humans have passed unfair judgment based on the superficial. And there was this brilliant study again about judges that would measure the severity of a punishment when correlated to what time of day the event would occur. They found that judges were more strict right before lunch, just as I was getting hungry and irritated, and the most lenient straight after lunch. But here's the rub. And I'm going to use another Hannah Fry quote. The outcome is biased because reality is biased. And we, as urban planners and designers, you know, wanting to use these algorithms to dictate large-scale and long-term features, must come to terms with this. So just to sum up this whirlwind intro to machine learning, we've talked about the three schools: the supervised, the unsupervised, and the reinforcement learning approach. We talked about how deep learning is a subset of machine learning, predominantly defined by the algorithms. And we've touched on very, very briefly some ethical considerations that you really need to think about when applying machine learning. You know, just because a computer said so doesn't make it so. And the outcomes are biased because reality is biased. So with that, does anyone have any questions before we wrap up this?
I would like to also add, before you go into the questions, thank you very much, Mel, because this was a great introduction to the participants that are not in the panel. You can also, like, if you want, use the Q&A to raise a question if you want. And if you want to come up and talk after the students, you can also raise your hand. So, but please. Nora, you were about to ask a question.
Yeah, I have one comment. Back when I was working on my master thesis at the Bartlett, I tried to debate between, it's like AI is right on the edge between using it as a tool or as an alternative decision maker for a human. So I don't know, what do you think about it? And also, how do you see AI as being used to go beyond optimization? How do you see it relate to optimization?
Sure. So I think the first point about if where AI sits. You know, is it a tool that is something we equip and use and wield, or is it something that makes the decisions for us? I think right now it's still incredibly up in the air and subjective. You'll see AI thought leaders argue both sides of the coin quite effectively, more effectively than I will right now. I think in the current state of things, AI is a tool for us. We are not in a position to allow the results, these models that we're putting together, to make decisions for us. Ultimately, we need to keep the human in the loop to validate what really comes out of the machine learning algorithm.
If I may add a point to that, as it's more like a general question. I mean, it's not necessarily about machine learning, but if we're talking about AI in general, I always like the distinction between weak AI and strong AI. So this is like something I really think is really relevant to that question. So I personally think that we, in architecture, because architecture problems are wicked problems by definition, and there's a great paper by Son Hanna. Since you're at the Bartlett, you probably know Son Hanna already. There's a great paper by Son Hanna and Lars Hesselgren and some others about why architectural problems are wicked problems. I can send that to you if you want. And the thing is that because they are wicked problems, we can't really expect a strong AI kind of like approach to it. Like we can't really expect an algorithmic, a machine learning process or some kind of other AI algorithm to come up with designs and with like designs that are like making sense for every aspect of an architectural problem. So we can't really expect AI to design for us, but we can definitely expect, as far as I believe, weak AI, so like machine learning, to give us answers to individual aspects of design, which we then combine with the ingenuity and the kind of like overview of the architect designer. So I would expect the AI processes to be, let's say, giving us a shortcut to answers, but it's not shortcut to design. It's shortcut to answers about design.
Interesting, thank you.
Anybody else?
Do you hear me?
Yes.
I have a question. At the beginning, when you cited with this historical observation, you cited, I don't remember the name of the guy.
Don Bradman.
Yeah, thank you.
Yep.
He said that machine learning is automates discovery.
Yeah. Oh, sorry. Yeah, that's Pedro Dominguez who would say that. Yes.
Yeah, automates discovery. And does it mean that you already know the answer when you want to research a topic or to solve a problem? I don't know.
Great question. Great question. I think what I do want to point out really quickly is that a quick distinction. The line itself was machine learning. It doesn't optimize discovery. It automates discovery. This idea of optimizing discovery is, well, I guess it could be same. I think the point here is that machine learning, automating discovery, is the process of finding new things, right? There's your question of does that mean we already know the answers? Well, no, not exactly. In fact, what Pedro Dominguez is saying with this line is we're now relying on machine learning to do this discovery for us, to give us the answers to questions maybe we don't even know. Perhaps that's a bit far-fetched coming from Pedro Dominguez. We don't know, maybe this is a bit, like we're not there yet, as a lot of machine learning is very heavily predicated on us defining the problem, defining the data set, having things ready to go and making sure it works as intended. But yeah, Pedro Dominguez is a thinker, and this is just, again, his interpretation.
I have a question. So I would like to just get your thoughts on something that I've faced while doing my research. It's so as practitioners or researchers, you require access to a lot of data.
Absolutely.
And specifically in the AEC, it inherently creates a lot of data, but there's a problem with democratizing it and sharing this. So what are your thoughts on the dialogue between municipalities or private stakeholders that generate and have the capability of democratizing this data and the responsibility in the users?
Yeah, I mean, you're absolutely right. Right. For some reason, we in the AEC struggle with machine learning because of data, but we generate so much data. The issue is it's often hidden behind privacy and ownership. Now, I've never worked as an architect. I've never worked in practice. I've only really just been a researcher. So I'm not sure how well I can contribute to this conversation. But my naive thought and my naive push to everyone here is that we should be the people making the change and pushing for this. You know, yes, we're machine learning engineers, and yes, we want to get all the data from all of these private companies, but we should also give back. You know, if we have our own data, put it up on a repo, let people have access to it, write some code, allow other people to use it. And so if we start, you know, pushing this idea enough, if we start doing this ourselves, well, we'll be the people then giving the data out, and you know, make the first steps to change, really.
As someone who has actually spent quite some time in a professional environment, I would say I completely agree with what Nari just said. I think it's a great point that, you know, the change comes from the people. 100%.
Thank you.
Well, if there are any other questions, feel free to post them into the Slack. Thank you so much for asking and engaging and listening to me ramble on. I think for right now on the schedule, we've got ourselves about a 10-minute break.
I would like to also say, if before we go into the break, we can start, like, we can, you know, start at 20 past or something, or like I don't know, 15 past. If anybody from the participants, from the attendees, from the auditing students wants to, you know, come up and say hi, or, you know, to ask a question in person, please raise your hand. We're welcome to everybody participating here. Yeah.
And side note, if anyone like from anywhere has a different opinion, you know, raise it up, like start the discussion. We are not the arbiters of truth. We are just sharing our opinion.
We can always mute you. Joking. So, well, we take 10 minutes and we come back 15 past. I mean, the live webinar will be still on, so you don't have to leave. You can still stay if you want. We'll be constantly here. All right, 15.
Cheers, guys.
See you at 15 past.
See you.
we come back. So Priyanka says she was kicked out. Okay, I will add her in the participants. 1 second. Did someone do that already, or?
Yep. Sorry, I did that. Yep.
Okay, thank you.
Thank you.
You're welcome.
I would like to also ask, perhaps, if possible, to even the attendees, if they can, to just like add their meaningful names to the list, so that we can verify that everybody who's attending is not like did not land here by a random Zoom link. So thank you for that. Now we will continue with an introduction to the machine learning models that we're going to see this couple of days, with Narid and Diosa, slowly waiting for everybody else to join. And then we will start looking into group forming. Yeah. Right, Narid?
Confirmed.
Yeah. So do you want to take over?
Oh, I think I'll hand it over to Yosh. Yosh, you want to share your screen? You're also muted. Yep, great.
Somehow we still have this bar here. Okay. Tell me when we are good to go.
Sure, let's start. Let's go ahead.
Right. Great. So, well, welcome back from the break. Now we're getting actually closer to start the actual workshop, the actual hackathon, and get you guys started on your little projects and work developing ideas for that. How to improve urban planning and design throughout technology and machine learning models and throughout the next few days in teams. As promised, we will provide you with a couple of tools and workflows and also some data. And we have a look at that in 1 minute. First, let's have a short overview on the structure we are right now. We will first present machine learning models we prepared. We do so with a strong focus on illustration, how it can be used in practice, and technical details that go deeper. We cover that tomorrow a little bit, but that's not really the focus here, as Narid already mentioned. Afterwards, Diosa will introduce this 3D city model, something like a playground model we prepared. You can use for context for your projects. You don't have to, but you can. And then it's almost time to get into the groups and brainstorm together on projects idea, and afterwards pitch it to all participants in the very end. And don't worry, we prepared a few sample projects and pitches for you can build on and orient yourself with. So anyhow, let's start. These are the 4 models, machine learning models we prepared for this workshop. We have Pix2Pix and DeepQ learning integrated in a Grasshopper workflow. And there you can train your own models and apply them on the Grasshopper workflow. Then we have Mask RCNN and style transfer models set up in a Google Colab environment, where you can use the pre-trained models with your own data. Let's start. Pix2Pix is a generative adversarial network that is capable to generate new images based on input images. And it's quite versatile and produce interesting visual results always. So it's quite fun to play with and experiment with to get a bit into touch into how to train a machine learning model and so on. You can use it in many ways. You can use it to approximate results of traditional simulations. You can use it to generate building footprints or floor plans, more on the generative track, and many more. We show some more examples later. Then we have DeepQ learning. It's an algorithm associated to reinforcement learning, and basically it trains a decision-making agent that acts strategically while trying to maximize some reward function we have to define. And there are again many possibilities, such as crowd behavior simulation, or for computer games to play tic-tac-toe against a human, or for instance to manage and organize dynamic systems such as traffic. And I think a real strength of deep machine learning is that an agent is not just purely reacting to the current situation, but also learns to take into account consequences that might come with a time delay. And this is what makes this behavior, the agent kind of strategically and the whole model very interesting. Then mask RCNN, I think we covered it a bit already. Basically, it makes computers understand the images and knows what actually is an image. For instance, here you see it knows how many cars there are and so on and so forth. And it's very important for applications such as self-driving cars, robotics, and many more. Finally, we have style transfer, which basically changes the look of an image based on a reference picture. In the urban context, we can use it to advance visual quality of images or answer questions such as how would this place look like during winter, rain, or things like that. Let's have a even closer look on each model. This is, we start with a pix-to-pix model, and you see the header of the original paper. It's definitely worth to check these papers out. They are usually really nicely written with many examples and backgrounds. So it's worth check it out if you're more interested in the details. However, we make it very simple. What does pix-to-pix do? What can you use it for? Basically, it transforms input image A here on the left side and turns it into an output image B in this case. And in this example, we give simple sketches of a street scene and buildings where each of these colored elements kind of represent a part of the building into the model, and it returns a more or less photorealistic image based on these simplified inputs. No. It just was freezing a bit. Am I ready? Computer? I think this is fine. Okay, this is another example. Sorry, my computer is very laggy. Okay, you see. Okay, hope it's stable again. Let's try this. Okay. Okay, I think it's fine. So here's another example of turning the image on the left side into something on the right side, a bit more abstract. We have on the left side kind of a density map. We can sketch in Photoshop or wherever of a road network, and then the model, based on that, we give it to pix-to-pix, and we get this kind of street network-like result out of it. And the animation comes by just blending two different density maps over and generate a pix-to-pix output for each of these combinations. Okay, here's another very interesting example. Here the author generate floor plans with pix-to-pix, with one addition that they stacked up two pix-to-pix models. So they start with building footprint. They train the model to generate a floor plan out of it. And then a second pix-to-pix model based on this generated floor plan adds details like tables and so on. So that this one gained quite some attention a year ago. Now, how does it work? How does the model, is the model doing this? Simply put, by providing it with lots of training data in the form of those kind of image pairs. So we always have an input image and a corresponding output image, and the model then, through a long training process and many data points, figure out how to relate these two images. You can put in everything you want or combinations. Some will work. If it's too strange, it will produce weird results. I think one guy tried out to combine pictures of ramen soups with faces.
Nice.
And obviously that, well, it didn't really was able to make any meaningful results out of that, clearly. Anyhow, now how can you use this? We uploaded a grasshopper definition where you can just download it, and with that you can create training data, image pairs. They are in the correct structure. So you only have to trigger the start training button, and the whole model should be start to be trained. And later you can use your trained model within Grasshopper and in your existing workflows. That was the idea here. I think quite many people of you use Grasshopper, so you can really build it into your own workflows and your experience of climate simulation or parametric modeling and so on. So I hope this will help you there. So again, the structure should be quite straightforward. Create training data, train your model, integrate it, use it. Let's have a few more examples and use cases. So let's say you encounter this problem. You need to count cars and satellite images on plants, but you don't want to do it manually anymore. So you could use a pix-to-pix model for that. And the first step is to create and structure your training data. In this case, the input image, we just take an original satellite image. And as a desired output image, we mark, highlight all cars with a green rectangle. And for the training data, we have to do it manually. Then I did this for 500 images of cars, started the training, and this is the result. Here, a new satellite image the model hadn't seen before was thrown into it. And this on the right side, you see the result. So the cars are kind of detected. Of course, it looks a bit similar, a bit different than the manual annotated one. And this is where you can see like the quality of your models. Let's check out another example. Someone might have the desire of making a generative model made in Grasshopper more portable by bypassing around Grasshopper this chunky software pieces, but keep the work and parts of the functionality from the parametric model in place. So one way to do this would be to use pix-to-pix again, obviously. So here we have a parametric model made in Grasshopper. And the idea is now that, let's say, a user on a website or something where they should be able to quickly generate some urban massings. The idea is they only have to draw 3 lines, street lines, like this blue lines on above image A, and then let the model create a whole urban design, so to say, out of it. So streets and buildings, blocks. By the way, they are here represented in red. So green lines are the streets and red are the buildings. And dark red means low buildings, bright red, high. So in this way, you can kind of translate your parametric model from Grasshopper into these kind of machine learning models. And in a way, make it more portable, sometimes faster. Or, yeah, I think there are quite some other ways why this could make sense. Anyhow, let's move to the next one, the last one. Let's say I want to find the ideal location for a local waste processing facility for each block in the city. So a local way of dealing with that. But using evolutionary optimization methods takes too much time and it's too much effort to set up for each of these blocks. So again, we could use a pix-to-pix model for that, at least to experiment with this. And here we have a simplified representation of our housing block on the left side, image A. And residential houses are now here represented as gray areas and potential areas for placement in black. Now for the desired output, image B, we ran a traditional optimization algorithm on that. And here with a very simple fitness function of maximize the distance to all residential buildings to place this waste treatment facility, because it's smelly and it should be as far as possible away from our inhabitants. So this is the result of our traditional algorithm. It would place the facility where this red box is. Now, we do that a couple of thousand times. Here is kind of the training data I generated with a very simplified generative model, but kind of does something like I showed before, more simple. And this is the result. So now on the left side, we move the gray boxes that represent housing, and the black lines here are places where we could place the waste treatment facility, could be a street or whatever, it's abstract representation. And on the right side, you see what the pix-to-pix model generates, and this red dots, this red agglomeration of colors is where it would would tell you to place this waste treatment facilities. I think what's important to see, you can really apply this kind of models for many different things. It's always about how you structure your input data, how you structure your input image and output image to tell the model to make this relation between input and output. So there's a lot of experimentation that can be done to figure out what works best. Yeah, and now I pass over to Nerit.
Yep. So the second of the two Grasshopper machine learning workflows will be the deep Q learning algorithm. What you should be seeing right now is a video playing. But first of all, what can it do? As mentioned, deep Q learning is a type of reinforcement learning algorithm, and reinforcement learning is all about training an agent within an environment to exhibit some kind of behavior with a little bit of reward or punishment. Maybe we should have downloaded this beforehand. So what the video is right now is a project out of OpenAI. It's known as competitive self-play, and what this should be a video, it's currently now a slideshow, is supposed to show is emergent behavior. And I think that's the true value that comes out of applying deep Q learning. What you should be seeing is two agents. These two agents are humanoid, and they are put into this environment of a ring. They are then rewarded for staying upright the most, and if their opponent is pushed over in the end. And at the start of the video, what was highlighted was emergent behaviors that wasn't explicitly taught by the human to the AI. It was something the AI came up with itself. Things like tackling or juking the opponent, where you would feign to the side and dodge. Another great example that I'd like to bring up for deep Q learning, just to really show what it can do, can we go to the next slide, is when it was applied to Tetris, the game of Tetris. An agent, which was was actually a controller. There was a reinforcement learning algorithm that was given control over the controller for a Tetris game. And one of the first emergent behaviors that came out of it was that it targeted a single side. Sorry, this isn't Tetris, this is Breakout. It targeted a single side so that the ball would go through all of the bricks to the back and then start hitting the bricks from behind. This was the more effective method. Could you go to the next slide? And deep Q learning is predicated on this loop here. Let's start on the right with the environment. Our environment will be within Grasshopper. So will the agent. The agent will observe the current state of the environment and then take that as the input of its brain, of its neural net. It then takes an action based on what it thinks is the best way to achieve the most reward. In the end, we measure this action. We see if this action was achieving some kind of behavior that we want, and then we reward and punish it accordingly. Go to the next slide. Over time, they should be able to develop some behaviors. So what we'll be providing to you is a Grasshopper definition that ties into a Python environment run locally, and which communicates back and forth through sockets. With this, you'll be able to visualize and hold persistence of your agent, your state, your action, and your environment. And within Grasshopper itself, you're able to define a sort of reward function to control or influence this behavior developed next. So a couple of examples of how you can use this. Well, the one that I started off with was to simulate the simple motion of an aimless car. The only objective is for the car to not hit any walls. So first off, we can use DQN by defining an agent simply being a top-down perspective, a rectangle, let's say, and how it perceives its environment with these lines protruding from the front. These are what I dub to be sight lines. And when these sight lines intersect with any geometry for the road, next please, that then influences what the agent sees. So after that, you can use this deep Q learning workflow to train agents that at first seem to move aimlessly, seem to just crash into walls, but eventually show some intelligible behavior, being able to dodge obstacles in the way and turn away from walls in the end. You can take this to an urban perspective and say you want to apply deep Q learning to allow a building to move around your site based on a bunch of different metrics. You reward it based on some sort of analysis, let's say some microclimate analysis. You want to have good solar performance for the entire plot, maybe good wind performance, pedestrian comfort, so on and so forth. This there could be your reward to influence the behavior of where this building should move and then be built. Question from the panelists: how long does deep Q learning take for the car? For this specific example, it was trained within an hour time period, and that hour was also including some tweaking of hyperparameters and so on and so forth. But it's a very simplified example. The agent itself could only make one of 3 options: turn left, go forward, or right. And I think this one was trained only for over 1,000 iterations here. But yeah. Back to you, Josh.
Great. I think we come back to this later. Now, the next model, Mask RCNN, state-of-the-art computer vision model, was also mentioned before, and it's capable of understanding image semantically in the sense of what an image actually contains. Here again, the model knows how many cars there are, how many people, and even how many shopping bags appear in this image. So you can imagine there are really many application possibilities. We prepared this in the Colab setup. Nero will guide you through this tomorrow in tomorrow's presentation. How to do it, very straightforward. You won't have issues with installing packages, which is very nice. So ready to go. And an example, let's say we want how to use it. I need a way to quantify the content of images of urban places in order to quickly find similar places. For instance, in terms of greenery, car traffic, pedestrian frequency, or building heights. Now, way we can use this Mask RCNN, we can use a pre-trained model from cityscapes, scrap a lot of street view images from the net, then run these images through the algorithm, and then we get results you can see here. We can detect persons, we can see how many cars there are, how many percentage of the image is sky, how many percentage of the image is a road or buildings, and so on. And from that, we can build a database. We can then easily query. If you have a new image, we run through the same model, and then we see similar models. I think we come back to this later for a sample project proposal for the teamwork. Another example I think we covered already is if you want to digitize a large amount of printed floor plans automatically, to use in the BIM environment or something else, you can use the same model as well as we covered before. Yeah, and now style transfer.
So the last of the 4 models at your disposal for the workshop is style transfer. Simply taking an image that possesses the content you want to show in the end, but applying a different style towards it. Next, please. Sorry, I can't click. And so we've, again, prepared a Colab environment. You don't need to worry about environmental setup. We've done all that. We've pulled a existing repo out there that's been in the community. Again, advocating for this democratization of machine learning, please. And we've tweaked some source code just so that it works in this environment. We're using NVIDIA's fast style transfer. And we've developed a workflow where you can upload or pull your own content images and style reference image so that you can apply this style on the content image. Where you could apply this is simply to quickly stylize a 3D model, let's say. Let's say you don't want to go through the lengths of rendering something. You have a 3D model in the top right there. You simply choose a style you'd like to apply and then apply it. This could be done in the urban context by taking a viewport of a street view image, so at the street view level, and then applying the style of a street view image for almost instantaneous, realistic renders, or I guess predictions of renders.
Yeah, so these are our 4 machine learning models. We hope you find them interesting. You find interesting ways to integrate them in your workflows, what you bring with yourself into this workshop, and maybe combine 1 or 2 of them together, which will also be very interesting. But I think for now, it's important to grasp and get an intuition how these models work, how you can actually use them in different contexts, what data you need to use which one of those. Because in the next steps, we're gonna brainstorm a bit on project ideas, as mentioned. And we would like to use these kind of models. But don't worry, we have some prepared, and also tomorrow we go through how to use them in Grasshopper, how to use them in Colab in more detail. So this will be guided. Yeah, next up, Diaza will tell you something about a 3D city model we prepared you can use for your projects as well. And I would like to hand over to her. Do you want to take the screen?
No, I don't need to.
Okay.
So now we saw some machine learning models. And to be able to apply these models in urban planning, we need a location, a map as a playground. So we provided a Rhino file, which you can find in the shared drive folder. The location of this place is in Vienna, in the center of Vienna, and the site is quite diverse. There is the Canal of the Nau River. And in the Rhino file, you can find data such as street network, building footprints and geometries, public stops, points of interest, etc. They are all given in layers. So considering all the data that the file contains, it's a little bit heavy. Therefore, I would suggest to personalize it and create a file only with the layers that you need for your project. And as said before, if you already have any other context that you want to use, of course you can. And next, please. Next slide. Thank you. Is this a video?
I see it.
Okay, nice. So, and together with a map in the same folder, you can find also a Grasshopper definition too. It contains a parametric urban model from which you can generate cases. And in the Grasshopper script is built also this interface that you can see in the left side, which makes it easy to see and toggle between the designs. Of course, you can adapt the definition, and you can use also different approaches to generate the cases. And next slide, please. But this is just example, so you can start working if you don't really want to focus on designing the site. And to get map data and their geographic features, we used shapefiles. Many geometries already had attributes. They are stored at the back slide, maybe, or
no.
The shapefiles, but it's. And for the shape, we put also the shapefiles all in the shared drive, and together with them is also one script how to import them in Rhino. And if you have any questions regarding that, you can reach us on Slack. And then the next one would be also another form to get map data is from OSM files. And for this too, in the drive folder, you can find the Grasshopper definition on how to extract the data. And included is also the library. You need to run the script. And there is also an example OSM file for Vienna. So various data can be taken from different sources and used in the project. And it's just important what kind of information you want to use for your model, and therefore to see which kind of data you need.
Yeah, so we hope to provide a nice selection for you. And well, now we basically have everything you need to the tools and the context model to start coming up with project ideas. But before that, let me show some example project and pitches we prepared. We arranged them like here. 5 examples, each of them using one of our machine learning models and parts of the playground you see here. So we have different topics, one generative models on the top left corner using pix-to-pix, 2 are more about optimization. One is using pix-to-pix, the waste treatment facility example we already gave. Then another one uses deep Q learning to optimize the position of a building, Nerrit was mentioning. And top right, we thought of using a deep Q learning agent to as a lockdown manager, basically, to say, hey, which times of pandemic, which amenities to close at what time while keeping economy more or less as best as possible, at least. The trade-off with healthcare and economy. And finally, project called Reference Renderer, where we would use mask RCNN to query I go into detail now. So instant master is an example of using a generative model in Grasshopper and training pix-to-pix with it to save time or to make it more easy to deploy in the web, for instance. And I think what I want to point out here is a structure. You could do your pitches, your project ideas, starting with a project title, then have a clear problem statement and a solution, how you would tackle this issue with your knowledge, with our models or whatever workflows you want to use there. And because later when you come out of the groups, it would be nice if each group has one or two of these kind of short and clear project proposals. This one we also covered, one-step optimizer. The problem is I want to find the ideal location of a local waste processing facility. By the way, of course, this can be anything. It could be how to place trees in a park, or like even where to place schools, maybe if you change the context a bit, and so on. And yeah, the pix-to-pix example. Another one here called AutoImmo Smart Building Allocator. Their the Q-learning agent would take over basically the building. So a designer can place a building, the red one here, and based on the context, it should improve its location. And in this example, to make a proof of concept, the idea is that the building should move itself around a bit to have maximize the view on this fantastic scenic area there, the park. And in action, this could look like this a bit. Here you see the building moving. This is for wind speed optimization, so not viewport viewing, but something similar. And this lines you see are as kind of the perceptive field, that is passed to the deep Q-learning model, and this is how this building and the agent perceives the environment. And yeah, this is how you can pitch in that direction. Yeah, the next one, here the idea was lockdown manager. And the problem in times of pandemics, it's crucial to decide which kind of amenities need to be shut down to maintain a balance between healthcare and local economy. However, the non-linearity of the matter and time delays between policy measures and infection rates make it hard for humans to make rational decisions. So in this project, we would use a deep Q-learning agent to decide when and which type of amenity to close and when to reopen it. To maintain, when you look on the left side, you would have like the red line would be infection rates, the blue line economy, to kind of keep the system more or less stable and not have like extreme outcomes. I think this is also a potential application possibility of this model category. Of course, it's a bit more complicated to integrate because you need kind of a background simulation to create the system the DQN agent would then observe and learn on. And finally, the reference renderer. With a problem when rapidly creating many different massing options, it's unfeasible to create detailed renders that try to imagine how a quarter would look and feel like from a human perspective. So the solution is that we first build a database of Street View images, semantically analyzed by a mask RCNN. And for each massing model, we then generate a simple perspective render that uses the same color schema used in mask RCNN. So trees would be green, buildings orange, like this kind of very simple color mapping. And then we can query out our database to places that look similar to our generated one in a very simple and fast way. Yeah, you can come back to the slides later on. We will have them up, and to get some inspiration, you can also use one of these projects to build on, or of course, always come up with your own ideas or mix everything up together. And yeah, I think we are really looking forward for your ideas and projects to populate this map. It would be a really nice presentation in the end. If we have many diverse aspects here, can also be experimental, that's no problem. And now, before we're having a short brainstorming session and discussion together, we will have another little break. And we will meet back in another Zoom meeting that is not being streamed. So it's just us participants. And there we have to have the possibility to have some breakout rooms, and we'll do the group work, distribute the groups, and have some brainstorming together.
Great, thank you guys. And so maybe some questions already before we go into break. I don't know if you want to address them now or after the break. What do you guys think?
We'll take questions about like structure and open-ended things, but anything more specific about specific projects, maybe we can save that for when we're in the room.
Yeah, I'm talking more about like, because after this, it will be like the rest of the discussion will be in the groups, and we will only come back here at the end to present and pitch. So I just want to make sure that we keep the participants, the auditing students in the loop in a way. So what will happen, because we can't have everybody in the meetings, so we will do the breakout and the rooms, the different like group forming in another meeting, and we will come back here to kind of like do a pitch. Or are we not doing that today?
We absolutely are, yes.
Yeah. So
for the participants, look into the hashtag workshop-links Slack channel. You'll see the link for the Zoom meeting rooms there. We'll see you in 5 minutes.
Yeah, before we go there, like let me introduce first of all here Theodore to everybody, and then we will, I think he's in the participants, in the attendees.
Let me.
Yeah, I'll promote him just now.
Did it?
We will be joining us for the group forming. And hi, Theodore. Can you see us? Theodore?
Hello. Hi, everyone.
Hi.
Hi, nice to see you.
So this is Theodore Gallans. We introduced him earlier, but now he will be joining us throughout the workshop. He will be advising us a lot, and so he will be joining now the group discussions. Just a small comment on like why we're gonna do groups. We are 25 people, so it's very difficult to give like individual feedback to every one of them. In 25 people, it's gonna be like much less time for everyone. So we need to work in groups by default. And well, the idea is, I mean, we have this, we have set up these like online spaces so that you can work together and we can work with you. And that's why like it's an idea of a hackathon. But it's not like it's not like a top-down decision, and it's not like, all of these group forming will happen from your side rather than from us. But we will talk about it in a bit. So you have them. I will actually post this here in the chat to only the participants, so that everybody has the link. Let me fetch it 1 second. I don't know if someone has it like ready, you can share it with just the panelists, perhaps.
I can do that.
Yeah, thank you, Nari.
Just the panelists.
And we will see you there in let's say 5-10 minutes, right?
Exactly.
See you all in that meeting. And to the rest, the attendees, we will see you back here in about, let's say, an hour, max 45 minutes to an hour. Yeah.
Perfect. See you guys soon.
See you soon.
See you.
Bye.